In this video, we will discuss function transformations. Essentially, what a function transformation is a way of creating a new function from an old one. And we'll see 4 examples in this video. And these 4 examples will go through a variety of ways that we can create those new functions. We can do things that affect the inputs, or we can do things that affect the outputs. And we can affect these inputs and outputs in either an additive way or a multiplicative way. So we'll see things like vertical shifts, where the function moves up or down the graph, horizontal shifts where they move left or right, a vertical stretch, and you can also do a vertical compression where the function increases in magnitude in the y direction, or a horizontal stretch. Of course, there's also horizontal compressions where the function stretches out in the x direction. So for our first example, we are going to look at that vertical shift, and we're going to start with this function right here that's sort of this W shape, and there's 5 points that are easy to track on this particular function, and I listed them at the table on the right. And with the functions that you transform from the library of functions, there will always be 1 or 2 points, or maybe an asymptote that you can keep track of. So you can either do so in a table or just remember where that particular ordered pair is. So the vertical shift that we're looking at is f of x minus 5. And first I should say a bit about how you recognize a vertical shift. So a shift in general is something that's additive, so you add or subtract a constant. If it affects the y values, it'll happen on the outside of the function. So here it's not in the parentheses along with the x, but instead it's on the outside. With the functions that you use from your library, you might be looking at a square root function or a reciprocal function. So if you have something added that's not under the square root or not in the denominator, then you know that that's a vertical shift. So what's this going to look like? Well, our initial table of values has these ordered pairs right here, and as we said, the vertical shift is not going to affect the x values at all, so they'll stay exactly the same. 1, 2, 3, 4, and 6. And what's going to happen to my y values as a direct consequence of subtracting 5 on the outside is those y values will decrease by 5. So I'll write f of x minus 5 here, and I'll take away 5 from each of the y values. And if I plot my new ordered pairs, what I'll see is a very similar shape that I started with. Let's see, 4, negative 3, and 6, negative 1 right here. In fact, the exact same shape that I started with, just transposed 5 units down the y-axis, and that's why we call it a vertical shift. One thing that I should point out is if I did plus 5 here, or if I did a plus instead, it would shift upward. And another thing that I think is important to recognize is the domain of the original function ran from 1 to 6, and the domain of my transformed function has not changed at all, because I didn't do anything to affect the x's. Meanwhile, the range of my original function went from 1 up to 4, and the range of my transform function, well, it has a low of negative 4, a min of negative 4, and a max of negative 1. So that's exactly 5 units below the initial range. So a direct consequence of shifting 5 units down. Our next example, we're going to look at a horizontal shift, f of x plus 4. So this is going to affect the x values. And the thing that you want to keep in mind about the horizontal shift is to recognize that it's still additive, but now it's on the inside of the function. So if you're dealing with that square root function, it's under the square root. If you're dealing with the reciprocal function, it's in the denominator, or it will be in the parentheses of the argument of the log, or whatever the function that you're using, the parent function that you're using from your library. So what's this transformation going to look like? Well, f of x plus 4, you might think, is going to shift it to the right 4, because we're used to plus being positive and indicating the positive x-axis here. But it actually works kind of opposite. The y values, of course, do not change, so we still have 3, 1, 4, 2, 4, but what you have to think about is what x's would you have to plug in here to get those same y values. We knew this ordered pair was true, that if x were 1, y were 3, but you can see now that into my function, if I plug 1 in for x, that'll be f of 5, and I don't know what f of 5 might be. But if I plug negative 3 in for x, then that would give me an input, like an eventual input of 1, and we know that that would lead to 3. So I basically, instead of shifting my x values to the right 4, I end up shifting them to the left. The inputs end up working backwards compared to the output. So if I shift 2 to the left 4, that would give me negative 2. If I take away 4 from 3, that would give me negative 1. And if I take away 4 from 4, that would give me 0. Take away 4 from 6, that would give me 2. So these are the new ordered pairs that I'll see in my graph. And let's see what the picture would look like. Negative 3, 3 here. Negative 2, 1. Negative 1, 4. 0, 2. And 2, 4. And once again, you can see the general shape has been preserved. What's changed is its position. It's shifted exactly 4 units to the left. So a horizontal shift of f of x plus 4 shifts it to the left 4 and not to the right 4. Again, if we take a quick look at the domain, my domain previously was from 1 to 6, and the range was from 1 to 4. While the range hasn't changed at all in my transform function, I have a new domain. My new domain goes from x equals negative 3 to x equals positive 2. And you can see that that's exactly 4 lower than my initial domain, 1 to 6. Take away 4 from 1, take away 4 from 6, and you're looking at a new domain. Because this only affected the inputs, so we only affected the domains. If you wanted to shift the function to the right, you would just use a minus instead of a plus. In our third example, we're going to look at a vertical stretch, and this will be a vertical stretch by a factor of 2. And again, this is vertical. It's going to affect the y values, and that'll manifest by showing a multiplication on the outside of the function. So not under the radical, not in the denominator, not inside the log, but multiplication on the outside of the function. So our x's again will stay exactly the same. Our y's will double in magnitude. And the picture that presents itself, instead I'll have 1, 6, there, 2, 2, 3, 8, 4, 4, and 6, 8, right about here. Well, it still looks like the same general shape. It still looks like a W. But you can see that the image has been enlarged, and it's been enlarged by a factor of 2. Right? And the other thing you want to keep in mind is how it's been enlarged. It didn't just like get wider and come down here below the x-axis, because it's not going to turn things negative all of a sudden. What it does instead is every single y value doubles in its magnitude. So it looks like it moves up the y-axis as well. And if we consider what happens to domains and ranges one more time, we know that the domain initially was 1 to 6, and the range initially was from 1 to 4. There's been no change whatsoever to my domain. But my new range now goes from 2 all the way up to 8. Okay, one last example. This one's going to be a horizontal stretch. So as we learned in the example with the horizontal shift, the horizontal stretch, or the things that affect the inputs are a bit backwards. So what we need to keep in mind here is if we want to stretch a function horizontally, well, you need to multiply on the inside of the function. But if you do so by a whole number, that actually wouldn't stretch the function. It would compress it instead. So the example I'm doing is f of 1/2 x. I'm going to multiply by a number between 0 and 1, and that will stretch it out because the x's, they work backwards. So my y's are going to remain exactly the same. Let's put my table down here instead. 3, 1, 4, 2, 4. And what we're asking ourselves is what values do I need to plug into my initial function to first get x equals 1, or to get the input to equal 1, which will give me an output of 3. So if I plug 2 in for x, that'll give me 2 times a half, which is 1, so my eventual input will be 1, and that'll give me an output of 3. So I must have the order pair 2, 3 on my graph. I'll plot it at the same time. And then the next question is, what value do I have to plug in for x to get an eventual input of 2 that'll lead to an output of 1? So if I plug 4 in, half of 4 is 2, and it'll give me an output of 1. The next question would be for 3, how to get an input of 3. So you can see the pattern here. I'd have to plug in 6, because half of 6 would give me 3. And then what about 4? I'd have to plug in 8. And then, last one would be 6, and I have to plug in 12. So if I plot these points as I go, like I said I was going to, 2, 3 right here, 4, 1 right here, 6, 4 right about there, that was convenient, and then 8, 2, and lastly 12, 4 right about there. So once again, we've preserved the shape of the W. But now, once again, it's gotten larger, not in the same way as the last example. The last example was stretched in the y direction. This one's stretched out in the x direction. Okay, so those are our 4 examples on function transformations. Just to recap real quick, vertical shift, you can shift the function up or down by adding or subtracting a constant on the outside. To shift it left or right, that's called a horizontal shift. To go right, we subtract the constant. To go left, we add the constant. A vertical stretch can be done by multiplying by a number bigger than 1 on the outside of the function. And you could compress by doing a number between 0 and 1. A horizontal stretch can be accomplished by multiplying by a value between 0 and 1 on the inside of the function. And if you multiply by a number bigger than 1, that's a horizontal compression. And last thing for today, quick game of Name That Transformer. You write these down in your notebook for tomorrow. Transformer number 1. Transformer number 2. Transformer number 3. So see how many of those you can get for tomorrow's class.